Welcome to Ask and Learn.
In this problem, we have a bullet that strikes a barrier, and that barrier is supported by a couple springs and a damper. And then once the bullet strikes the barrier, there is a total mass, capital M plus little m. And so this is the mass of the barrier here, and we have spring constant, damping coefficient, and then the bullet coming in. And then it embeds, so we get this total mass. The natural frequency then is 2k divided by the total mass of the system, or the square root of that. Now they said to determine the dashpot for critical damping. So critical damping is when the damping ratio is 1, and that is the square root of the equivalent damping, which is just C, divided by 2 times the equivalent stiffness, which is 2k, times the equivalent mass, which is the total mass of the system in this case. So we can solve for this, and we get that C is this value here. We can pull this in, and this becomes an 8. But we can, if we wanted to, if we knew what these two things were, if we knew what all these were, we could figure out what C is. And now since it's critically damped, we know our solution is given by this expression. The funny thing with critical damping is it's really a mathematical artifact. You're never ever going to get zeta to be exactly equal to 1 in practice, but it's a decent approximation to try to get something that doesn't. When you have something that's critically damped, so if you plot the displacement versus time and something hits it, it will come back and it will never cross 0. So it will just slowly decay back to 0 here, but it won't cross. That's true for all, whether it's critically damped or over damped. Now, this case with critically damped is that it will come back the fastest without overshooting. So that's kind of one of the cases a lot of times where you design for. If you want something to return back to where it was, but not overshoot, but return back as fast as you can, you design it to be critically damped. A good case of that is a door mechanism, an automatically shutting door mechanism that you'll see in lots of buildings. That will you want the door to shut fast, but you don't want it to slam. So you want it to be roughly critically damped, so the door, once it's opened, it just kind of slowly, but comes back to rest at its closed position, doing that as fast as it can, but not smacking into the door jamb. So we know the bullet hits this thing. The initial displacement is 0, and the initial velocity we can get from conservation of momentum. So initial displacement being 0 says that A is 0, and the initial velocity being the mass of the bullet divided by the total mass of the system, the bullet and the block, equals the velocity of the incoming bullet. And so that means that's what equals, so if we take the time derivative of this, set t equal to 0, it just becomes B, and so B is this expression, and that means that our equation governing motion is here, and I didn't plug in omega n, but we can plug it in here. So we have everything in terms of k, little m, and big M, and the velocity of the incoming bullet. Now they asked us to find the spring's maximum compression. So we need to figure out when the velocity is 0. So we can take the time derivative of this, and that gives us this expression. At t star, that's going to be 0. So that's where the displacement will be maximum. So at t star, we get this expression. This is not 0, unless either the mass of the bullet is 0 or its incoming velocity is 0, but we're not considering that case. This is also not 0, so we can divide 2, and basically we find that the time when the velocity is 0 is 1 over the natural frequency. So we can then plug this back in to get the maximum displacement and do a little simplifying, and we get this expression here where we get the mass of the bullet divided by E, Euler's constant, and then the square root term times the velocity. So we can see that the maximum amplitude increases linearly with the mass of the bullet and the velocity of the bullet. So if you double the mass of the bullet, you're going to double this. If you double the velocity of the bullet, you're going to double this. And then it depends on, well, I guess the mass of the bullet is also in here, but in reality, this is going to be very small compared to this. So anyway, then, if you increase K or M, then these things, this is going to decay. This is going to be smaller. This is going to go down as we increase the stiffness of the springs and the mass of the block.